Can you see my presentation?
Yes, sir.
Yes, sir.
In the last class, we have started discussing learning system, and we have seen that there are some informations, essential information or essential attributes that are needed to design a learning system. Okay, so for example, we have seen that how training experience can affect a learning system based on the training examples. Okay, and there are a few more attributes which are also found to be important for designing a learning system, like the target function, and then a representation of the target function, and finally we need to have the function approximation strategy, so that will optimize the performance so that we can get the best result, or the result which we desire. Now the question is how to choose the target function. So if we see any learning systems, this learning system will depend upon two major factors. One is the type of the knowledge that we use, and how we can use this knowledge to enhance the performance. Okay, so these two factors are very important for a learning system. Now when we design a learning system, so we need to determine exactly what type of knowledge can be learned. Okay, what type of knowledge can be learned, and how this knowledge can be used to enhance the performance. Now to learn the representative of a large class of tasks, like in case of the example that we have seen in the last class, the checkers playing game. In checkers playing game, what we do, we make a large class of tasks. So what is the task? So task is to find a best possible board state. Okay, board state means after every move of the pieces, so we can have a new state. Okay, so we can have a new board state. So in this way, if we collect or if we gather a large class of such tasks, so that will define a large search space. Okay, so search space means this search space will be known as priority. So this information need to be available to us so that we can design the learning system in better way. But there is a problem with this large search space, that when we use this information as a priority, so it is very difficult to find the best search strategy among this large number of search spaces. Okay, so this is very difficult to find the best search strategy from this large search space. Okay, now how do we do this? So we can take help of optimization algorithms or optimization strategies, so that will help us to find the approximated to the best search strategy, so which will be also helpful to design a learning system. And also when we use this search strategy or the optimal search strategy, then obviously the performance will be enhanced. Now not only we choose the target function, but we need to choose a representation of the target function. So we can choose many target functions in many different way, but what would be most suitable for a learning system, so that we need to know. Okay, or that we need to determine. So this is called the representation for the target function. That means we need to determine a representation of a large number of target functions which are being determined from a large search space, so that we can apply this representation for the target function, and we can have the best result. Okay, Now in case of checkers playing game, we know that the task is referred by the playing checkers, and performance measure P is referred by the percent of games that won in the tournament or in game. Okay, and training experience E is referred by games that played against itself. Okay, or played against humans. Okay, and that here the if we consider the target function is v, so we can have a large number of board state, okay, after every move. Now if we carefully check a board state, a particular board state, then what we see? So we need to collect, or we need to gather the feature information. So what would be the features in case of checkers playing game? So for considering every board state, we can have a large number of features. So features like, so there are two different type of pieces. One is the red color pieces and black color pieces. Now, if we consider one such feature like how many red pieces are available on the board, how many black pieces are available on the board, and how many red pieces are how many red pieces are threatened by the black color pieces, or how many black color pieces are threatened by uh, red color pieces. Okay, and how many kings are available on the board? Red color kings and black color kings. Okay, so these are the information, so which can be referred as the features, so features of a particular board state. Okay, now if we consider such features for a particular board state, then we can have this linear combination of such features. So here we could define a representation of the target function, which is referred by this v cap of b. So this is the function for the representation. So this representative function will be selected for the possible target functions. So here w0 to wn, here w0 to wn. So w0 here is the coefficient, or we can say the weight. Okay, and here xi is the features, particular features. Now if we find or if we determine n number of features for a particular board state, then we can have this linear combination of these features. Okay, and these linear combinations of these features are taken with the weighted coefficient. So weighted coefficient means this weight is determined from the training model, and this weight is determined according to the importance of the features in a particular board state. Okay, so this would be referred as the representative function for the available target functions. Okay, now the last attribute is the function approximation algorithm. So here here we could have the function approximation algorithm, and this function approximation algorithm is characterized by two different information. One is the estimating training values and adjusting the weights. So how do we estimate the training values? If we consider the checkers playing game, so how do we estimate the training values? So here the training examples is the number of board states. Okay, and every board state will have some features. Now if we try to quantify the board state in terms of the features, then this will be called the training values. Okay, now we can consider the checkers playing game, and to estimate the training values by quantifying every board state in terms of number of features which are available on board state. Okay, so this is the first type of information that need to be available to a function approximation. And another information is the adjusting the weights. Okay, so how do we adjust the weights? So we need to adjust the way such a way so that we can optimize the performance and get the desired output. Okay, optimize the performance. So we can have large number of possible options from which we need to select the best possible option. So best possible option will lead us to the optimal solution. Okay, so we need to adjust the weight such a way we can have the optimal solution for the problem.
Sir,
Yes.
sir, adjusting the weights means that we have to adjust weighted values for every board states.
Yes. So
And
that means
yes,
every board state will be updated. If we consider the current board state and consider the available features on the board state, then in the next iteration, what will happen, that board state will be updated. Okay, board state will be updated by the next possible features. Next possible feature means the in the next board state we will have some other values of the features. Features will be unchanged. The number of red pieces, number of black pieces, number of red pieces written by black pieces, number of black pieces written by red pieces, number of red kings, number of black kings. So these are the available features, but the features values that we quantify, so that may be different. Okay, for every possible board state.
yes, sir.
Okay. Now we will take an example of a learning model and we will try to understand the different components which are involved in a learning system or learning model. Okay. Now in this example, we have taken a supervised learning model. So as you know that the supervised learning model uses the labels. Okay, labels means the class levels or class information. Now, initially, what we have initially, we will have the if we consider the if we consider the analyzing system or text analyzing system. So in this case, we can have the training test. Okay, training test, documents, images. So this text will be analyzed from the images, either from the documents. Okay, so initially this will be used as the knowledge. Okay, knowledge base means uh, this will be our database from which we will extract the features. Okay, and these feature vectors, so this is our feature space. This is our and this will constitute the feature space. These feature vectors will constitute the feature space. Okay, and from this feature space, if we have some available learning model, then we can model these feature vectors to a training system or training example. Okay, so these training examples will be used to model the system that is called the supervised learning model. Okay, and this supervised learning model will be the examples of the supervised learning model will be labeled by this class information. So class information is available to this machine learning algorithm. Feature vectors are available to this machine learning algorithm. Then we can build a trained model. Okay. So here we are building a trained model. Okay. So this machine learning algorithm will be responsible to construct a learning model or trained model. Now this trained model will be used to classify the text in the document or images. Okay, so these training examples are used to build up this training model. Now we will use the new examples. New example means these are not the labels example. Okay, these are not labeled. So initially we have the training use the training examples and with the class information that is called the labels to build up this training model. After constructing the training model, now this training model will be used to classify the new text which are available in the documents and images. Okay, now from this unknown text, we can also have the feature vector. We can construct the feature vector, and this feature vector this feature vector will fit to the predictive model. So this predictive model is nothing but the f cap x. Okay, f cap x means the approximated function, or the function approximation is referred by this predictive model. Okay, now using this predictive model and the trend model, we can classify the new text which are available in the document and images. Okay, now this text, this unknown text or new text will have some label after it goes through the predictive model. That means predictive model will be responsible to find the new labels for the unknown text which are available in text and images. Understood? If you have any questions from this part, you can ask me. Okay. So now we will start studying the regression models, and to understand the motivation of regression models in machine learning, so we will take an example. So here the example is the population growth problem. So that we consider here to understand the motivation behind regression models which are used in various applications. Okay, so if we see this population map, then we can see that this population map is estimated estimated until the 2100 years. That means until these years we have predicted the population. So now, what are the different features that we can use to model this world population problem or the population growth problem? So, if we consider a data set of Indian population growth data, then we will see that for a particular year we are considering the population growth figure, okay, and the growth rate. So this was started from 1950, okay, 1950. So until 2022 we have this figure of population growth and also the growth rate. Okay, now to understand the regression model, and if we select a particular model like a population growth model or population growth problem, then using regression models we can find a better solution for population growth rate, uh, so that we can find, or we can estimate the future populations in different continents. Okay, so in this example here you can see that here we have divided the population growth rate uh, on in different continents. Okay, so if we see the growth rate of Asia, then we can see that after certain period of time this will get decline. Okay, but in case of Africa we can see the population growth is gradually increasing, and also the future estimated figures also show that so it will be increasing gradually until 2100. Okay, and for other continents we can see that it is been saturated over time, and it get declines. Okay, now considering this data, population year, population growth figure, and growth rate, if we consider these three different attributes on population growth rate data, then we can model this population growth problem, by using some regression models, okay, or regression techniques. So here initially we can use the regression models. So what type of regression models we can use? So if I simply consider a linear regression, or the equation of straight line y equals to mx plus c, okay, and then we will try to fit this data in the linear regression model or linear regression equation. So what would be your x, what would be your y, what would be your m, what would be your c? If we try to model this population growth problem using simply linear regression, not logistic regression or multinomial regression or multilinear regression.
Sir,
So what would be your dependent variable? What would be your independent variable? What would be your model parameters? Here the intercept and slope both are known as the model parameters. Okay, and x is known as the uh, independent variable or explanatory variable, and y is known as dependent variable. Okay.
sir,
Yes.
sir, y is the population, and
Y is the
sir,
population. Okay.
sir, m is the population growth.
Now, aim, we need to determine the aim from this population growth information and growth rate information.
Yes, sir. And sir,
Because model parameters are not available with data. Model parameters like intercept and slope, we need to determine from the available data. Okay.
sir, x
Only,
is the time.
okay.
Sir, x is the time. I mean the year we are trying to predict.
Okay.
And so c is the just before year. I mean the year just before the previous year. I
No,
think.
you know how to compute intercept and slope. If you
Yes, sir.
know that, if you know that how the available information like independent variable and dependent variable both can be used to compute the slope and intercept, then then we could determine the model parameters, slope and
Yes, sir.
intercept.
Yes, sir.
Then after determining the model parameters, then we will consider this available data. Consider this available data means if we consider the growth rate or population growth rate as y and growth rate as x, okay, then for a particular year, for the particular coming years or future years, we can estimate the population growth. So this population growth is represented along y-axis and growth rate is represented along x-axis. Okay, if we do this, so can we solve this problem? So this population density or population growth will be determined over time. So over time means, yeah, if we consider the years along x-axis, now we need to associate some data with this year so that we can use the corresponding data for determining the model parameters. So what is that? Population growth or growth rate? That need to be associated with the year because we represent
The
the
growth
year
rate,
along
I think.
x-axis. We represent the year along x-axis and we represent the population growth along y-axis. Because population growth problem is the exponential population growth happen in exponential way, okay, or exponential. So exponentially, if the population growth is happened, then we need to figure out the model. So what will be the model? So there is a available model, so which can be used to get a solution for this population growth problem. So if we consider an exponential solution for this, then we can have this r and n. So here n is nothing but the population density we can consider, or the population growth in a particular region. If I consider a region is a country or a district, okay, or a particular area, so this n will be referred as the population growth and r is the growth rate. Okay, so r is referred as growth rate. Now, this dn by dt, that means if we find the derivative of population growth over time with respect to time, then this will give us the rate of change of population growth. Rate of change of population growth. Okay. Now, if we think this problem in another way, then we can have this solution. Okay. These solutions can be formulated by logistic function. So what is logistic function? So logistic function, basically this logistic when we use the logistic function to solve some regression problem or the problem at hand, then what we do, we find some L-shaped curve. This is called the L-shaped curve. This is also known as the sigmoid curve, okay, or sigmoid function. Now, to use that regression or use that logistic function, so we can formulate the population growth problem in this way. In this way means, if we consider some parameters like here we have the population growth figure, we have the growth rate, okay, we have this is called the capacity carrying, okay, or we can say the carrying capacity. K is referred as carrying capacity. Carrying capacity means the number of species that can sustain in a particular environment. So if we consider if we consider the human species, then if and also if we consider a particular area, so in that area how many human species can sustain over time in a particular environment. Okay, so that means we need to consider the available resources also. Okay, available resources also, we need to consider the population growth figure, we need to consider the growth rate also. So now now if we use the logistic functions and try to find the rate of change of population growth, then uh, we need to find this derivative function. That means we will take the derivative of population growth with respect to time, and this will give us the rate of change of population growth. Okay, so essentially we need to use these three informations. Basically we are using two informations. So one information will be associated with the time, okay, time means here the year, okay, and another information that we can use as the independent variable or the explanatory variable. Okay, so this is not a this is the simplification of this solution. That means if we consider the linear regression, that is y equals to mx plus c, and we will try to fit this population growth data in that linear regression, then we can have some simplified solution. But that is not desired. We need to consider few other parameters, so which are based on the available resources in a particular region, okay, or in that particular environment. Now we can start from least square regression. Now this least square regression is very much useful to understand many other regression models. So if we start from least square regression, so there are few reasons uh, behind selecting this least square regression to understand the different regression models. Okay, now what are those reasons? So we can find it very useful. So we can find it very useful to uh, understand the underlying model assumptions in many applications. So if we consider this regression model to understand the underlying model assumptions, so this will be found to be very close to the some method, so which has been widely used in some in many scientific domains or many domains that we are working with. Okay. Now, if we analyze the least square regression thoroughly, then we can use that use that information or use this understanding to see other regression models, and we will try to understand what is going on in those regression models. That means if we analyze the least square regressions very well, and if we consider the closed form solutions, then obviously this will help us to understand the other regression models in better way. Okay. Now it also enables the transformation of classification problems into regression problems. So which is an approach taken by logistic regression and neural networks. So as I said in the last class that if we consider two different strategies, logistic regression and neural networks, now the understanding of least square regression will help us to transform these two different techniques, logistic regression and neural networks, from classification to regression problems. Okay. Now, the thorough understanding of least square regression would help us to understand the relevant topics also. Relevant topics means where we can, the applications where we can apply the regression models with different machine learning strategy. So that will also help us to understand the solutions to the problems using least square regression. Okay. So this is the starting point. If we consider this is the starting point, then we will when we will go through different regression models, or we will come across different regression model, then we will see that the general framework which is used in different regression models are found to be close to the least square regression. Now, if we consider the general framework for any regression models, then we need to learn a function. So what type of function that we need to learn? Because this function need to be learned for the model assumption. Okay, model assumption of not only linear regression but also for other regression models. Now, if we consider this function is f, so this f is defined this function f is defined over m dimensional data. Okay, so here rm is m dimensional data. Okay, now if we consider there is a vector xi in m dimensional data rm, then we can define a function f of xi over this particular feature vector. Okay, now this function is nothing but the nothing but the inner product of features and the model parameters. So this theta 0 to theta m are nothing but the model parameters. Okay, and this xi1 to xim are known as the explanatory variable or independent variables. Now this function may be the dependent referred as the dependent variable. Okay, that we need to determine from the data in terms of the explanatory variable or independent variable and the model parameters. Okay, so in case if we consider linear regression, in case of linear regression, these model parameters would be the slope and intercept. Okay, now if we get the inner product of these two information, the two information means one is the explanatory variables, another information is the model parameters, then we could get the linear combination of both this information. Okay, linear combination of both this information. Okay, so here you may consider theta 0 is comparable to intercept. Okay, and rest of the equation is comparable to mx. Okay, mx plus c in linear regression. Okay, this is your y, this is your c, and rest of the equation is comparable to mx. Now the dimension of these model parameters would be m plus 1. M plus 1 means after considering the theta 0, so theta 1 to theta m is m, and m plus 1, see this one is we are getting this one because of this theta 0, and theta 0 is nothing but intercept in linear regression. Now we are considering this observed data which are to be fitted in the framework as yi equals to f theta of xi plus ei. Okay. Now what is this e? What is this ei? So we know about this. We know about this component. We know about this component. But what is ei here? Can you tell me what is ei here? Can you tell me what is ei here?
Sir, loss function?
Hmm?
Loss function?
Yes. Yes, loss function. So how do we get this loss function? Or how do you compute this loss function? So we need to determine this loss function from this
Sir,
regression.
yes, yes, sir. For regression problems, sir, loss function, we can square error loss or absolute error loss. Two types of loss we can compute.
Yes, there are two different types of loss functions:
Hmm.
square error loss and absolute error loss. Okay, or absolute error function.
Yes, yes.
Now, if we consider this framework with n observations, suppose there are n observations. Okay, now these n observations we can fit in the regression model with the help of this formulation. So what is this formulation? So in this formulation, y would be the dimension of the y would be 1 to n. That means there will be n number of dependent variable, there would be n number of dependent variable, there would be n number of explanatory variables, and there would be n number of loss or n number of errors. So that would be generated from the regression model. Okay, now if we further try to explain this framework in terms of explanatory variables or independent variables and the model parameters, then we can see that this would be reduced to this formation. This would be reduced to this formation, means y equals to capital X theta plus e. So other way we can write this formulation in a compact way, and the compact form would be y equals to capital X theta plus e. What is y here? y is the y
Sir,
is the approximated function.
yes, sir. Yes, sir.
Predict basically this is the predicted value that we are going to determine. Okay, this is the approximated function, and this capital X is referred to the independent variables, collection of independent variables or explanatory variables, and this theta is referred as model parameters. Okay, and this e would be added to this component so that we can determine the loss function, or we can compute the error which is generated from the regression model. Okay, now here what would be the dimension of this x?
Sir, n into n.
Hmm? Why?
No, sir. Sir, n into m.
n into m plus n or n into m. N is the dimension for
So why?
n is the dimension for y and e.
Yes, sir.
Okay, and for the model parameters and the independent variables, the dimension would be m plus 1. Okay, so n into m plus 1.
Yes, sir.
That means the number of rows would be number of rows would be n, and number of columns okay, number of rows would be n and number of columns would be
M plus 1.
m plus 1. Okay, so this m plus 1 into m. So this is the dimension of the X matrix. Now, if we have given m plus 1 parameter vectors theta and the linear model predict the dependent variable at point xi. So here xi, if the xi would have this much of features. Okay, so if the dimension of xi is m in the feature space, then we could get the response. Okay, response means the response would be 1 comma xi into theta. 1 comma xi into theta. So this would be the response in the regression. So if we consider m plus 1 parameter vector theta, okay, and the linear and the point xi is having m dimension data in the feature space, then the response of the linear model would be 1 comma xi into theta. Okay, now the difference between the actual response yi from the observed datum xi comma yi and the predicted response would be, so this is the difference between the actual response and the observed data. Okay, so yi minus 1 comma xi into theta. So basically we are subtracting the actual we are subtracting the approximated value from the actual value, or the approximated outcome from the actual outcome, and then we get this error. So error function is defined over the deviation between the actual value and the predicted value. Okay, now using the training risks as an estimate of risks, searching for a minimum risk approximation to f theta is equivalent to searching for a parameter vector theta, so which can minimize the training risks. Okay, now after determining the loss function, now what we will do, we will try to minimize the training risk. Okay, minimize the training risk. Now in terms of this estimated loss and the deviation between actual value and the predicted value, we can define the training risks, so which will minimize the error in the regression model. Okay, now this training risk can be defined by n into r train a theta. So this is the training risk for n dimensional data. Okay, n dimensional data means we will take the sum of the squared distances, so here yi minus 1 comma xi1 to xim, and that will be multiplied by the transpose of these model parameters theta 0 to theta m. Okay, and this will give us the residuals sum squared. Residuals means the which is left over. Okay, so in regression model, what is left over? This is the leftover ei. Okay, and we are taking the sum of squared of residuals or sum of squared of leftover. Okay, so this equation is known as the residuals of sum squares. Residuals of sum squared. That means in other way we can say the sum of square of residuals. Okay, So this will give us the square error loss, which is determined from a regression model. Okay, so this is the very basic. This is the very basic loss formulation that we can determine in any regression models when we work with some uh, machine learning problems or the problems at hand. Okay, so this would be defined over this loss function in terms of the actual value and the predicted value, and this would be called the residual sum squared. Okay, or we can say the sum of squared as sum of squared of residuals. So here we are taking the initially for every data point we find the deviation, we take the square, then we find the linear combinations of all sum of all these squared of all data points. Okay, and this would be defined as the training risk, which will minimize the error in the regression model. If you have any questions, you can ask me. If you have any questions, you can ask me. Otherwise, we will stop now.